Today, what we're going to be talking about, what are some of the basic building blocks behind many of the current recent NLG methods, specifically transformer and some other stuff. Then we're going to be talking about large pre-trained models, different learning paradigms, so few-shot and zero-shot learning, and finally about text editing models, which is an area that I've done a lot of work myself. Yeah, and then next week we're going to be talking a bit more about how to deploy these models and so on. One thing we didn't have time to cover last week, but I promised to do this week, was about side projects. So kind of, if you're anything like me, at least during my PhD, I was thinking a lot about how much time should I invest into various side projects. So I had a lot of ideas and a lot of things I wanted to try, but I wasn't always sure, like, if it's a good idea or if I should just strictly focus on my PhD and making sure that I finish that on time. And okay, this is of course very anecdotal, but at least in my case, well, first of all, my professor was very supportive of me doing these side projects, and I think in the end it turned out well for me. So I'm happy I did explore a bit. Some of the reasons being, first of all, which is perhaps also a bit sad, is that pretty much all of my side projects ended up being far more popular, at least in terms of citations, than any of the papers I did for my PhD. I would still say that I'm quite proud of the papers for my PhD, because technically many of them are, I consider them of being higher level than the side project papers. But at the same time, I'm very happy I did pursue these side projects also. So for instance, last week I talked about the DeepBeat project for rap lyrics generation. So this one specifically, I think it may have even have a slight tiny help with me getting into Google. So I remember when I interviewed for Google, my first interviewer actually said right at the start that he had come across this project because it was in the news. And at least it gave me a lot of confidence. I guess it didn't really affect the decision so much, but at least it didn't hurt, I felt. And in general, when you think about how much should you do your side projects, I think it's this traditional trade-off between exploration between different topics versus exploiting the ones that you've already kind of done some work on. One reason maybe why you may want to consider trying out different things and doing some side projects, at least especially in the beginning of your PhD, is that often you don't see the impact of a given paper or of your work immediately, but it takes time to see how people react to it and if they start building on something on top of it. So in that sense, it makes sort of sense to diversify your research investments. And then over time, you see which things work, which things you enjoy yourself, and then it might be easier to make an informed decision on what to focus more. And at least I myself noticed that whenever I tackled a new problem, it kind of forced me to learn a lot of new things. So in that sense, it was very useful. But after saying all of this, I should also note that if you just do, let's say, one paper per project and then you move to a new topic, that's probably also not a great strategy. So if you want to really build a reputation in a subfield, for example, if you want to focus on academic career, then it's really important to, I would say, to have multiple good papers in that field so that people start to recognize you and yeah, and so on. Okay, this is my personal opinion take. Feel free to ask more about it if you're pondering these same type of questions later. But let's then move to the actual topic of today's lecture. So first of all, I would say probably many of you already know transformer, but if you had to name what's the most transformational innovation in the field of NLG or in the NLP in general within the past, say, 5 years, I would probably say it's the transformer. Maybe another contestant would be BERT, but even BERT is very, very heavily based on or built upon transformer. So in that sense, transformer is a more fundamental technology. And And in this lecture, well, we won't have time to go into all the details of how transformer works. I think some of you have already taken, for example, the deep learning course, which I think dedicates a full hour or maybe a full lecture to going through the different details of transformer. I very much recommend, if you don't have previous experience with transformer, I recommend you to learn more about it. So for example, there's of course the paper. I found the paper when I first read it not too easy to kind of get all the details. So there's also this annotated transformer, which is basically the paper plus some code snippets that give you some more details of how the different components of the model are implemented. There's the illustrated transformer blog post, which I found very useful, and we're basically going to use many of the figures in this post when we're talking about transformer today. But so my goal is kind of, we won't be going really into all the math and details, but kind of give you the practical introduction of when you're applying transformer, what are sort of the key characteristics that you should be aware of. All right, so let's go right into it. So transformer, first of all, it's an encoder-decoder model, or often these are called sequence-to-sequence models as well. So encoder-decoder model means that, first of all, you have an encoder stack, which is responsible for converting your text into continuous numerical representation. So essentially it maps each of the tokens into some kind of embedding, a vector representation. Then you have the decoder part, which is responsible for converting these vector representations into text output. And some of you are probably familiar with the RNN, or recurrent neural network based models. So there are also RNN based seq-to-seq or encoder-decoder models. But I would say that today these transformer-based models have largely overtaken the RNN-based models. Not completely, there's still use cases for the RNN-based models like LSTMs and GRUs, but there are some practical advantages of transformers. For instance, the training of these transformer models parallelizes very nicely. And just at least in my own experience, when I entered the NLG field, in the beginning, I would usually always train both an LSTM-based model and transformer, and very consistently the transformer model would outperform or at least be on par with the LSTM-based model. Also, since we're at Aalto, I just wanted to mention, probably many of you are aware, but one of the pioneers and prominent figures in the field and with the encoder-decoder models is Kyun-Hyun Cho, who's an alumnus of Aalto. So he has developed, for example, this GRU architecture, which is an RNN-based encoder-decoder model, and also attention-based encoder-decoder models. Okay, but so let's look a bit more closely into what goes into a transformer. So I already mentioned, you get some text. First, these are mapped into continuous representation or vector representations. They're passed through the encoder, and then the decoder attends to these encoder outputs and produces text outputs by using a linear and softmax layer at the end. And before looking more closely into what goes inside to these encoder and decoder stacks, I believe some of you have already studied. So would anyone be able to tell me what's the difference between the initial embedding that you get after? So basically, first you look up an embedding vector for each token, then it goes through an encoder and get a different kind of embedding. So what are sort of the main differences of these two embeddings? Why do you need the encoder in the first place? So the main difference, exactly as you said, is that the encoder makes the embeddings contextual. So in language, the meaning of the word, there's a famous quote that goes something like you know the word by the company it keeps. So it's not just the word itself, but the meaning is defined also by what's around it. So that's why it's important that you kind of build in the context when trying to represent a given word. The other difference is that what you see in this figure is that it shows that these embeddings are use this with time signals. So you add some kind of positional embedding to the embeddings because unlike the RNN-based models, now you have no kind of notion of order of the input words unless you add this position embedding. So it kind of informs you, it's unique for its position so that you have some kind of notion of the order. Right. Okay. So these are the main two differences. Then if we look a bit more closely into what goes into the encoder and decoder, well, we won't go through now all of these different components, but the first thing to notice here is that the encoder stack and the decoder stack, well, they both contain of multiple layers of similar architectural components. And the encoder and decoder stacks are actually very similar. So they have similar, both of them have self-attention, these feed-forward networks, and some layer normalization, and so on. But the main difference between the encoder and decoder is that decoder also has what you see here as the encoder-decoder attention. So self-attention means that, and we'll talk a bit more about it soon, is that you kind of attend to the neighboring words in the input or in the output, while the encoder-decoder attention means that the decoder attends to all of the encoder outputs. All right, and the other main difference between the encoder and decoder is that the self-attention, when you attend to the neighboring words, you cannot attend to the future words because basically that's what you're generating. So you use this kind of causal masking that you mask even during training when you actually know the future words. Now you mask these out and you only attend to previous words. Okay, and the attention, so there are two types of attention. Like we mentioned, there's the self-attention, and then in the decoder, there's also encoder-decoder attention. And these make the representations contextual. The attention mechanism is multi-headed, meaning that there are, so basically you have different heads which kind of attend to different type of things. So in this figure, you see, for example, these orange bars, which show that when you compute the attention, you compute some kind of weight for the neighboring words. And then based on this weight, you kind of bake in some of the representation of these neighbors into the current representation. Case where this would be important, if you have, for example, a pronoun like it, this attention might capture the antecedent. So what does the pronoun refer to? In this case, it would refer to the animal didn't cross the street because it was too tired. So it would refer to the animal. And this is what the first attention head captures in this example. All right, I already said we use causal masking in the decoder. And then finally, one thing that's important to know in practice when you want to apply this is that, as you can see here, all the words attend to all the other words, which means that this is going to cause a quadratic complexity. And this can be the bottleneck when you start having long sequences. So the transformer won't be anymore very efficient because of the quadratic complexity. Okay, so the things I kind of hope you to take away from this, this was not just we're just scratching the surface, but what transformer does, it produces contextual word representations via self-attention. Yeah, actually one thing I didn't really highlight yet, but it's an autoregressive model. So the way that the output is generated it's done one token at a time from left to right. And this is also, this can become a bottleneck. So one nice thing about transformer is that the training still parallelizes very nicely in contrast to the RNN-based models, but during inference, you still have to do this prediction, the output words one token at a time, because then you condition the future predictions on what you predicted previously. So that's why the inference can still be slow. Encoder and decoder stacks, they're similar apart from this encoder-decoder attention and the causal attention masking in the decoder. And finally, there's the quadratic complexity caused by the self-attention. And this quadratic complexity, in this course, we won't be talking more about it, but there are, in the recent years, there have been many developments on kind of removing this bottleneck, so making the attention computation subquadratic. So there are models like reformer, linformer, longformer, and many others that are actually able to compute the attention in linear time, or in log n. Okay, if you're interested, go ahead and take a look at the links in the slides, but otherwise I won't be covering these more in this lecture. So, but let's start looking more closely into what are some of the modern architectures, or what is kind of state of the art these days. And the first thing to notice is that, as I said, transformer has been very fundamental technology. And from what you can see is that many of the current architectures are based on, or they're different kind of variants of transformer. So just to list few of these, first of all, there are different variants also in terms of whether you have the encoder or decoder or both. So there are some encoder only models, like BERT is a good example. And BERT is not really developed primarily for NLG, but it's used, as we'll see in this lecture, as part of some NLG methods. Laser Tagger, on the other hand, which is some of the work we did a few years ago, it's developed specifically for NLG, and it's an encoder only model where you essentially predict the outputs independently, or the output words. And in that sense, it's similar to the, there's a quite popular line of work on non-autoregressive machine translation. I'm not sure if it's fair to say that these or some of these works are encoder only, but often it's the case, at least, that there's a very shallow decoder while most of the computation is done on the encoder side. Then there are the encoder-decoder models, like the original transformer model, but some more recent ones include T5, which is very popular, BERT from Facebook AI research, which is also a very popular one, Mina, which is a dialogue system, and then finally decoder-only models. GPT is probably the most well-known, but some of the more recent ones include Clam and Gopher, which is actually, I think it was published just a few weeks ago, but it's one of the largest these days. All right, so in this lecture, I'll talk a bit more about the following methods that are highlighted in this slide. But many of these other methods are actually in the list of seminar papers, so I hope that some of you will be selecting these and we'll learn more about them during the seminar. Also, like I said, this is going to be pretty high level overview of these methods, but then during the seminar, we'll be looking more into the details, hopefully, as we'll have more time. But before I go into these methods, one thing that is usually common to all of these methods is that they all follow the similar type of training pipeline, which is that first you apply some kind of unsupervised or self-supervised pre-training, meaning that you have some large corpus of unannotated text, so you don't have any labels, but then you create some self-supervised objective, like you hide out some of the words and try to recover them based on the context. And the idea of this kind of large-scale unsupervised pre-training is that it helps the model to learn to represent the text better. And also it kind of teaches the model how does text look like, and makes essentially produce more fluent output texts. Then after the pre-training, you do fine-tuning on a small, usually much smaller data set of labeled input-output examples. And as an effect of this pre-training, you usually don't need as much fine-tuning because the model has already learned a lot about the language. So it basically just need to learn the task and not things like what does a grammatical sentence look like. Also, another thing to note here is that we'll mention few pre-training tasks now when we'll go through into some of these methods, but there's also a lot of work on tailoring the pre-training tasks to resemble the downstream fine-tuning task. And there are a few works, for example, Pegasus paper for text summarization, which shows that this can be more efficient or effective than just using the same pre-training task for all the final tasks. Okay, so let's start with BERT. So as I said, BERT is primarily intended not for NLG, but for NLU-like tasks like sequence classification or tagging or span prediction. But why it's relevant to mention here is that actually the pre-training objectives in BERT, they're very much related to NLG. So the first pre-training objective in BERT is called the masked language modeling task, where you mask out some random words from the input sentence. And now this input sentence just comes from some large web corpus. And then the task of the model is to predict what's the mask token. Okay, so that's the first task. Then the second task is called the next sentence prediction task. And it is formulated as a classification task so that you concatenate the sentence with another sentence where the other sentence can either be the true next sentence or some randomly taken sentence. And then the model is taught to predict whether it's the true or not the true next sentence. In the paper, they do some ablation study where they leave out this next sentence prediction and their numbers go slightly down. But some later work has found out this is actually not such a crucial part. So many of the follow-up works don't use this NSP task anymore for pre-training. But it seems that the main benefit is really coming from the masked language modeling task. And in the paper, they trained this on Wikipedia and a books corpus. Okay, then the next method to look into is called T5. So T5 is an encoder-decoder model, and it kind of studies, well, it's quite a long paper and studies many different things, but kind of the main focus is on transfer learning. So they try to teach a model that does many tasks at the same time. And as you can see in this example, the model tries to solve tasks like machine translation, then some kind of NLU tasks where you need to classify the outputs. And what is kind of interesting, it even tries to solve some sort of regression task where you need to output a numerical sentence. So you see this yellow box on the rhino grazed on the grass. And then you need to output some kind of similarity between the two sentences in numerical format. And what T5 does, it's a text-to-text model. So everything is represented as a text. And even these numbers, which at least to me sounded like a very dirty hack when I first saw this, even you map even the numbers to strings, and you basically round these floats into one digit with 0.2 increments. But okay, it seems to work quite nicely. So they get very good results. And then the idea is that you train the model on many of these tasks at the same time. So another thing that this paper puts a lot of effort is into comparing different kind of pre-training objectives. So you have sort of the fine-tuning objectives, but then you have also various pre-training objectives, and they essentially compare different variants of, for example, the masked language modeling task, where you delete some words in the middle and then predict them as output. So just to mention maybe one of these is that in BERT, you replace individual tokens with masked tokens. So if you delete 2 tokens, you replace it with 2 masks, like what you can see here or here. But then what D5 does is that it removes spans in this IID noise replace spans. It replaces the whole span with a single special token, and then each span that is deleted gets a separate special token. Then the output just contains the special token and then what was deleted. So this is what the decoder is supposed to output. Okay, so comparing the pre-training task is one thing. Another thing they show is that it's useful to scale up the pre-training data from, so BERT used just Wikipedia and a books corpus, while T5 uses a C4 corpus, which is also publicly available, which is based on crawled web documents. And one thing I think which has made this popular is that they release pre-trained checkpoints of different size. So usually this pre-training stage, it's much more expensive than the fine-tuning. But now that you have this pre-trained checkpoint, you only need to basically do the fine-tuning, which you can do very quickly. And this has yielded many state-of-the-art results on various NLG tasks. There are also some variants of T5, for example, MT5, which is the multilingual version of T5. Okay, then let's move to GPT-3, which is probably the most well-known text generation method these days. So first of all, GPT-3, it's a successor of GPT-2 and GPT models. And the main difference between these, so there are small architectural changes, but they're pretty similar still. However, the main difference is that each of these successive variants of GPT has been much bigger than the previous one. So for instance, GPT-3 has over 100 times more parameters than GPT-2. And GPT-2 already produces quite natural looking text, but GPT-3 is even better. Like I mentioned earlier, this is a decoder only model, so there's no encoder stack, but whatever input text you want to condition on, you basically use it as a prefix that's fed to your decoder and then just continue predicting from this prefix. I listened to some interview of Ilya Sutskever, who's the chief scientist of OpenAI and one of the authors of the GPT-3 paper. And when he talked about the prefix language modeling task, he said something along these lines. So if you predict the next bit really well, then you have extracted all the meaningful information. Therefore, you should have a representation of all the concepts. So here he's kind of giving motivation for this pre-training task and saying that in order for model to be able to predict the next words accurately, the model needs to learn to represent the concepts that are mentioned in the text accurately. So to kind of give you some idea why this kind of pre-training is useful. Okay, so let's take a look at a few examples of what GPT-3 does. There's this, so OpenAI, it's the company that has developed it. They have this API for this. And I think initially you had to be waitlisted to get access to the API, but I tried it quite recently and I could get access directly. So You can also go ahead and try it out. There's a link at the bottom of this slide. But so what I tried here was to give a short prompt, the course recent advances in natural language generation will, and then ask GPT-3 to complete this prompt. And okay, so what it writes here is the course will be taught by Dr. Antoine Borde. So he's actually quite a well-known figure, or very well-known figure in the NLP field. Then it says something like the course will be an introduction to main research challenges and recent advances in the field of natural language generation. Well, that's correct. The course will be delivered in English, correct again. Then it talks about the topics, and there are things like generating text with attention that we've covered, applications in NLP, text summarization. So actually, I would say this is a very coherent output, and it actually kind of corresponds to what we are actually discussing at this course. Of course, not exactly. And if you start looking more closely, you see things like, as I mentioned, this Antoine Borde is a real person, but at least as far as I know, he's not the founder and chief scientist of the LISA lab. He's, as far as I know, he's a director, but at the Facebook or Meta AI Research. And okay, some of these topics that the output mentioned make more sense than others, but generally I would say this is a very nice output. Okay, so this gives you an idea of what the model does. So it can generate very long and fairly coherent outputs, but of course it also does make mistake. Now, what I would say, so one of the things the GPT-3 paper does is that it radically scales up the model size, and they show using some automatic evaluation that it's beneficial to increase the model size. But the reason I think, and what really made this paper such a significant, and at least in my sense, it sort of introduced a paradigm shift in the field of NLP. I'm not sure if it was strictly the first one to do this kind of fusion learning without fine-tuning the model, but at least it very much popularized this idea. Okay, so what do we mean by fusion learning without fine-tuning? So in the paper, they give many examples showing that you can actually use the same model without having to fine-tune the model parameters to solve a wide range of tasks. So let's take a look. First, before we talk about fusion, let's talk about zero shot. So zero shot means that you don't have any training samples to teach the model how it should solve a given task. But rather you just basically describe the task. So I wrote the following description: find a rhyming animal name, word heap, rhyme, and then I asked the model to complete this. Before I show you the model output, I just want to make sure that this is a task that's solvable by humans. So can any of you think what would be a correct completion for this given task? Sheep, yeah, exactly, great. So it's a feasible task. Sheep, it does rhyme with heap, and it's an animal name. So that's exactly what I had in mind when I wrote this description. What the model outputs here is not sheep, but it's sleep. And this is still pretty good. It's a rhyming word, and it's not totally obvious that it rhymes in the sense that it has different vowels than heap, but it is indeed pronounced in the same way. Okay, but the model doesn't really catch the part about it having to be an animal name. Okay, so that gets us to, yeah, it's pretty close. It has an edit distance of 1, but still conceptually very different from sheep, I would say. Okay, but this gets us to the fusion paradigm. So what it means that now what you would usually do is that you take a few examples, then you kind of start updating your model parameters so that it would learn to output the given outputs for the given inputs. But now you don't touch the model parameters at all. You just provide the few training examples as part of the input, as part of the prompt. So I gave the following examples. For the cake, the output should be snake, mock, dog, fat cat. And given these inputs, the model actually does output the word sheep that I was looking for. And at least to me, this is quite an impressive example of the capabilities of the GPT-3 model. Okay, and yeah, maybe still to say a few more words about why this is so significant that the model can do something like this, is that essentially this allows you to build something like this public API where you don't have to, for each use case, you don't have to have a different set of model parameters. The fine-tuning itself can be quite time-consuming and inconvenient. Then you would have to keep in memory all these different sets of parameters and always choose the right. But now you just have a frozen set of parameters. The clients can just provide whatever prompts they will, and then you just run inference with no training. Okay, some terminology. So this task description, find a rhyming animal name. That's the task description. Then you may have some examples in the few shot domain, but then in the zero shot, you would not have these examples. Then you finally have the prompt. I think sometimes prompt refers to the whole thing, but in this case, prompt is just the current input that you want to, for which you want the model to provide the output. So one of the things they find in the paper, they compare different model sizes, and they find that increasing the model size does not only improve performance when you fine-tune models, but it also improves the performance quite significantly in this kind of a few shot setting where you don't do any fine-tuning. However, if you don't have huge resources, good news is that some other researchers have found out that you can actually do similar type of few shot learning even with much smaller models. So there are a few different papers from Timo Schick and Henrik Schütze that show that you can use, for example, masked language models to solve various text classification tasks, even if these models have much fewer parameters than GPT-3. And we also, in the list of seminar papers, we have one of their papers where they apply these kind of smaller models to the NLG domain. Okay, one sort of meme that came around with GPT-3 was about whether all of us ML engineers will eventually just become prompt engineers. So the thing that people found out was that it often takes some trial and error to get the optimal prompt. So the model outputs what you want. And also there are memes like the one you see on the right, where like in the early days, you would always have to build special purpose hardware to solve a given task. And then with software, it became just about designing the algorithm for the task. With the introduction of machine learning, you wouldn't need to develop different algorithms, but you could use the same ML models, but you would just need to provide a new data set for the model to learn the task. And now the next step would be that you don't even need to provide the data set. You just need to write a good description of the task in natural language, and then the model will basically solve your task. And of course, then if you think, what's the next step? So as I said, this writing the task description, it still requires some trial and error. So a natural question to ask is, can we also automate this part in some way? And this is sort of the task that some of the recent works have looked into in a line of work called prompt tuning, where the idea is that you try to use the same benefits that I mentioned earlier of having a frozen model that you can use for different tasks. And then you try to learn prompts that are specific to the task. Now, in this case, the prompts are not necessarily of natural language, but they can be what we call soft prompts. So they're just some basically word embeddings that you input to the beginning of your model input. So you kind of prefix your input with these small learned prompts, and yeah, and basically then the model is kind of these sort of tune the model to solve the right task. And one of the other nice or benefits of doing this kind of prompt tuning that some of the papers found out that this may transfer better to new domains than if you were to tune your model parameters. Before we go to the next family of methods, I wanted to say something about decoding strategies that I didn't really cover when we talked about transformer earlier. So when you want to actually generate output from these models, first of all, the space of possible outputs, it's very large, as you can imagine, because you have the size of your vocabulary to the power of the number of tokens of different possible outputs that you can get. So it's not usually realistic, or it's not realistic to find the sort of the optimal output among all possible sentences. Usually the objective that you're trying to maximize is the likelihood of the output that you can decompose into likelihoods of the individual tokens in the output condition on the previous tokens generated so far. And now the way you go about maximizing this in practice, or some kind of heuristics, one very common heuristic is a greedy approach, where you would always select the most likely next token, and then when you're generating the next token, you condition on the most likely next tokens generated so far. Another that usually gives you a bit better, or kind of more likely outputs, but still is not guaranteed to provide the global optimum of this task, is called beam search. And this is a heuristic where you always keep the k best solutions generated so far, and then you run the model for each of them to generate the next output, and then you again compute the k best and repeat this until the end. And then finally, so the first two are something if you just want to maximize the output, but what some of the works, and if you ever train these models, usually what you see in the beginning, especially if you're using a non-pre-trained model, is that in the beginning the model provides very dumb output. So it might, for example, be repeating the same word, like the all over again, or repeating the same phrase many times without ever finishing. So if you, in order to get more diverse outputs, there have been different methods. One of the well-known ones is called nucleus sampling. Yeah, which basically modifies the distribution and then samples from it. And if you want to just do something like some creative stuff, generate random stuff, this is a very nice way of doing that. Okay, if you're interested, feel free to take a look at the paper. The link is in the slides. But let's then move to the next family of methods, which is the text editing models. As I mentioned, this is an area that I've done a lot of work. It's maybe like not the most, not the hottest topic in the academia right now, but I think it's a very important field. It's a very important field in the sense that these text editing models have some very nice practical benefits, especially if you want to deploy these models. So namely, these are usually very sample efficient. You don't need a lot of training data to fine tune these. And the second is that they're very fast to run, because some of these are not autoregressive, but you can actually run them in a feed-forward manner. So, and to give you some background, last week we talked about the problem of sentence fusion, which kind of motivated us or led us to develop some of these text editing models. So to quickly recap, sentence fusion is the problem where you have two or more answers and you want to fuse them into a single coherent answer. So for example, you might have these different aspects about Albert Einstein's birth and death, that you want to summarize into a sentence like Albert Einstein was born in 1879 and he died in New Jersey at the age of 76. And when we first tackled this problem, our kind of natural first approach was to just take a transformer and train it on transformer. Back then, this was maybe 2018, there weren't so many good pre-trained checkpoints yet available, so we had to train it from scratch. And this transformer model, it worked fairly well, but then sometimes it would just produce some new facts, or it would hallucinate, or just produce very unnatural text. And the reason we concluded was that we simply didn't have enough training data, because we didn't at that point have a good way of generating automatically large scale of training data. So the next step we took was that, first of all, we made the observation that usually in sentence fusion, there's a very high overlap between the original answers, so the input, and the fusion, so the output. So in order to produce the fusion, you mainly need to just delete few repeated phrases and add some short glue phrases between the inputs. So this led us to develop a text editing solution where, instead of predicting the output from the scratch token by token, we would rather predict edit operations that are applied to the input tokens. So what do these edit operations look like? We have 3 basic operations for this particular task: keep a token, delete it, or pronominalize it if it's an empty dimension. And then in addition, on top of each of these base operations, we can add a phrase before the current token where the phrase comes from predefined vocabulary of possible phrases that the model is allowed to add. And this vocabulary of phrases is usually something small, can be just a handful of phrases or up to 500. Usually there's a way of optimizing this set of phrases automatically. And by the way, this paper is one of the possible options for the seminar. So we might go a bit more deeply into this if one of you selects this paper. One kind of nice benefit of having this phrase vocabulary is that it gives you a control and guarantees of what the model can introduce. So it cannot introduce arbitrary new text, but it can only introduce stuff that's in the phrase vocabulary. And for the pronominalize operation, it also gives us some control, in the sense that when the model predicts to pronominalize an entity dimension, we can actually look up, for example, the gender of the entity from a knowledge base and then select the appropriate pronoun based on that. Okay, so how does this work in practice? You have an input text. First you encode, so you kind of produce an embedding for each of the input tokens, and then you predict the tag for each input token, where the tag corresponds to an edit operation. So for this particular input, you might predict to keep each of the input token, except for deleting the period in the middle or between the 2 sentences, replace it with the word and then pronominalize the second mention of Turing. And then finally, you have a realization step where you apply these tags to get the output, like Turing was born in 1912 and he died in 1954. Okay, so this is a high-level overview of how the method works. Then into some of the results, or maybe before that, now how this is implemented in practice. For the encoding part, we can use naturally BERT that we already discussed earlier. Okay, so in the paper that we published, we ran a comparison between lazy attacker and then an encoder-decoder model transformer, where we initialized both the lazy attacker's encoder and the transformer's encoder with BERT. And the main finding we made was that these 2 approaches yield a pretty similar performance when you have 45,000 training samples or more. But once you go below that, the performance of the seek-to-seek or the encoder-decoder approach, it dramatically drops. So if you have just 400 training samples, the output of the model is just garbage, essentially. Whereas the performance of the text editing approach, LazyStacker, it degrades much more gracefully. So even with just a few hundred training samples, you can still get pretty decent outputs. One of the things I didn't mention yet, we compared two variants of LazyStacker. So one that is fully feed forward, so you predict all the edit operations totally independently, and then another where you have a shallow decoder, so you have just the one layer transformer decoder on top of the encoder. And in this case, we found that in general, the autoregressive variant with the transformer decoder, it performs slightly better, but there's not really a big difference. However, there is a big difference in terms of inference time, so the feed-forward version is much faster to run. And in terms of efficiency, we compared the transformer model and the LazyStacker model, and we see very significant speed improvements for the inference time. Another nice advantage of the text editing approach was that sometimes the transformer model would again hallucinate. So for example, if it saw some weird words in another language, it would just make up some words, whereas the text editing approach would not be able to do this because it wouldn't have these weird words in the vocabulary in the first place. All right, so now we talked about some of the benefits. There are, however, limitations, of course, to this. First of all, sometimes the realized text is unnatural because although we do use pre-training, but we only use it on the encoder side. So the model has not really learned a good model of what does a natural looking output sentence look like. But it only relies on the training samples to learn this part. The other limitation is that, well, a benefit of this limited phrase vocabulary is that you have sort of more control and you don't hallucinate so much, but then sometimes, or for some tasks, this is just too restrictive. So for example, if you want to do things like grammatical error correction, this can be a problem because there are so many different ways that you can introduce grammatical errors that you need to then be able to fix, that it's not ideal to have a limited vocabulary. And then finally, for tasks where reordering of the input words is required, it's not very convenient because then you have to first delete the word or phrase at some position and then insert it from the phrase vocabulary at another position. So to mitigate these limitations, we had a follow-up work paper a year later. The method was called Felix, where the idea is that you separate the insertion part from tagging. So first you have a tagging model that just predicts which tokens to keep and which tokens to delete and where to insert stuff. And then you have a separate insertion model that at given positions inserts stuff. Now the nice thing is that the task of inserting words at given positions, it's actually exactly the task that BERT mass language model has been pre-trained on. So we can just use a pre-trained BERT checkpoint to solve this task. However, if we do have some training data, fine-tuning on that, of course, helps. But now we can leverage this unsupervised pre-training to get more fluent and grammatical outputs. Another idea that goes into Felix was that it has a separate reordering component. So there's a pointer network that predicts the order of the input tokens. Still, the nice thing that all of this is done in a feed-forward manner, so this is still super fast to run and therefore useful for practical setups. And we saw big improvements over LazyStacker on several tasks in the paper. Okay, so that's it about text editing. There are a few papers in the seminar list still around this topic. The next thing I want to mention before we wrap up the lecture part is about tokenization. And I would say that tokenization is not maybe it's a very underappreciated topic, but again, it's something that's of great practical importance. So you should be familiar with this if you're working with NLG or with NLP for that matter. But I think it's more important certainly for NLG. So what is a token? So token is the smallest unit of text that you feed to your model. And why this is of great practical importance is that something that I can say from my own experience is that you notice that after you've already pre-trained your model and run the fine-tuning, then you notice that there are some inputs actually where the tokenization is really bad. And we'll see maybe some examples of what does a bad tokenization mean. But then you realize that you may need to do the whole pre-training, which can be very expensive and time-consuming, and the fine-tuning from the scratch if you want to change your tokenization. And this is particularly important for the text editing type of models that I just presented, because there the operations are applied at the level of tokens. So then if your tokens don't make sense, then it's hard to come up with good edit operations. So for instance, if you do something like grammatical error correction, you may want to change the suffix of a word. So if the suffix was a separate token, then it would be easy to just replace this suffix token rather than replacing the whole word. Another area where these are usually important is when you want to internationalize your models. So for example, if you will have models for some Asian languages where there are no clear word boundaries, then it's very important what sort of tokenization you use. Or if you work with morphologically rich languages like Finnish, then tokenization again becomes very important. And some of the different types of tokenization that people typically use. So I would say traditionally, people have tried to come up with vocabularies where the items or the tokens corresponds to words. More recently, there are some subword level tokenization methods that we'll talk about more soon. Then, especially in Finland, there has been done a lot of work on morpheme level tokenization. So there's the Morphers tool, which is well known, that's been developed at Aalto. And then recently also there have been some even more fine-grained tokenization works where the inputs are split into characters and bytes. Okay, so now please pay attention. So I wanted to ask you something. Okay, Katja is writing there will be a lecture on morphology in the SNLP course. That's great. So if you're attending this course, please pay attention, because yeah, actually one of the interesting topics is using these morpheme-based tokenization systems with current architectures. And I think there has been some work being done in comparing morpheme-based tokenizations and subword, but I'm not sure if the kind of findings are very conclusive yet. If you're interested, there's one paper in this field in the reading list. I'll mention a bit later. Okay, but let's look at sort of two extremes. So one extreme is using full words as tokens. So for example, untokenized text, you would split into untokenized text and a period. Then at the other end, there are the character level or byte level tokenizers, where each of the characters would become its own token. Now, can you think of what would be the disadvantages of each of these two approaches? So if you use word level tokenization, what will you suffer from? Okay, character level tokenization, Hamad is writing, would be good for rare unseen words. Yeah, this is a great point. So if you have rare words and use word level tokenization, you might encounter a lot of unseen tokens or unknown tokens. Okay, so that would be a disadvantage of the word level or an advantage of character level. Are there any downsides of character level tokenization? Sean is writing that characters can introduce misspellings. Can you elaborate a bit on what you mean by this?
For example, instead of outputting whole words, if you output character by character, then there is more chance that one character can be wrong and then the whole word gets wrong, compared to if we like just output words, then probably if the words are good, then we always have like at least well-spelled words.
Yeah, this is a great point actually, which I think I don't list, but yeah, indeed. you have sort of more guarantees that you'll output something grammatical when your tokens are full words. Good point. Okay, I see. Okay, word level tokenization allows for longer context windows. Yeah, this is one very important aspect, that because when you split into characters, your sequences become much longer, and then usually you have a fixed sequence length, something like 128 or 512 tokens. So you cannot have as long context when you use characters. Yeah, Katja is writing characters also don't bear meaning. Very good point. So when you try to model the character on its own, it doesn't bear meaning. So the modeling task becomes harder. Yeah, others are also writing that the characters result in longer sequences. Indeed. Character level tokenization has a smaller vocab size. Yeah, this is a good point also. Why vocab size is relevant is that usually you have something like an embedding matrix, which can like be a significant part of the model parameters. So having a smaller vocabulary will give you a smaller number of parameters in the model. Characters contain less information. It will provide less representative feature. Exactly, yeah. So that's why, yeah, it makes the modeling task harder if you use characters. Okay, thanks. Yeah, these are all very good points. So let's see if we already actually covered everything. Yeah, a bit more about, so yeah, words. If you use words, in order to cover all possible words, especially if you're working again with something like morphologically rich languages and you want to cover all the possible word forms, you end up having huge word vocabularies. And even then, you're very likely to encounter some unknown tokens that you simply didn't have in your training data. And this results in a lot of model parameters. Yeah, one practical aspect. So characters make the sequences longer, which means that you cannot have as long context. But if you do want to then increase your context size, then it will make your training and inference slower. There are some recent works on character level models, namely Byte-D5 and Charformer. So there are some ways to mitigate some of these limitations, but these are still not they still have their downsides. So I would probably say that the state-of-the-art methods, at least for many tasks, are still not character level models, but for some tasks, like it can be good for example, for morphological inflection and tasks like this. So what I would say is the most popular approach these days, which is in between these two extremes, is subword segmentation. And now there are different algorithms for optimizing these segmentations. So the commonly used ones are BP, Unigram LM, and WordPiece. And just to mention one aspect of these is that, or kind of desirable aspect, is that the subword segmentation is reversible, which means that when you've tokenized your text, you can go back to the original text with a separate detokenization method, so you don't lose any information on, for example, which tokens have a space before them. And one kind of case where this does not hold is BERT's WordPiece vocabulary. So BERT loses some information on whether a certain punctuation should contain space before it, which doesn't really matter for NLU usually, but if you want to use, for example, the masked language model for NLG, then this becomes a problem. So you might need to create your own vocabulary and rerun the BERT pre-training if you want to use it for NLG effectively. Another small kind of but important practical aspect, that even with the subword tokens, like when you move to non-English scripts, and there are often some weird characters that you don't end up having in your vocabulary, but they support what is called byte fallback. So you could always fall back to one of the 256 bytes, so that then you essentially never have unknown tokens. And typically, I would say that vocabulary sizes are somewhere between 30,000 tokens and 250,000 tokens. If your model needs to be applied on multiple languages, then you usually need larger vocabulary. Okay, so that's what I wanted to say about tokenization. Then, so to wrap up the lecture, the things I hope you take away from this lecture are, first, so transformers, they're really powerful, and most of the state-of-the-art methods are some sort of variants of transformers. And there are different variants in terms of the specific architecture. So for example, what kind of layer or normalization you use there. But then there are also variants on a higher level, like whether you use both an encoder and decoder or just a decoder. And in order to get a high model quality, two crucial things there are, one that has been shown in the previous years is that pre-training plays a really big role, and also increasing the model size usually brings large quality gains. A second relevant aspect is about sample efficiency or data efficiency. So how much training data you need to reach a given model quality. Here again, pre-training helps with the sample efficiency a lot. GPT-3 paper shows that also scaling up the model size helps with the sample efficiency. And then finally, we saw that another approach to this is to cast the problem into something simpler, into a text editing problem, where the output space is much smaller. You don't have to optimize over all possible sentences, but you just optimize over the sequence of edit operations. And this makes also the methods more sample efficient.